Hello dear students. So yesterday we have seen what is the idea of enthalpy, few basic laws of thermodynamics, how we can apply those laws in addition to the hydrostatic equilibrium condition. So we have stopped the lecture at the discussions of enthalpy. So where we have identified a specific quantity which is called as H plus phi, where H is the enthalpy. Enthalpy is also defined as the total heat content of the system, and H plus phi is the geopotential. So we managed to combine the enthalpy, that is CPT, and the total and the geopotential to identify the heat that is given to the system. So this H plus phi is known as the dry static energy. Right. So this dry static energy is relevant for the discussions of air parcel or for the discussions about the movement of air parcel in an adiabatic environment. Okay. Dry static energy. Right. So here we will take home this particular physical quantity H plus phi, and we will try to understand how we can use this to understand how we can use this particular dry static energy to understand the movement of an air parcel. Right. We will try to understand before we will try to see what is an air parcel. The most important thing is if an air parcel, if a volume of air which is considered under certain conditions moves in the atmosphere with respect to height, let us say, such that it is not allowing any kind of energy transfer between the surroundings and the environment that is inside the air parcel. So in that case, it is naturally expected that this dry static energy will remain conserved. I mean, it will be a constant in an adiabatic picture, right? So we will try to see what is the consequence of this conservation, right? So before, let's see what is an adiabatic process. So in majority of the discussions that we have in atmospheric physics, we always take the process to be adiabatic. The movement or the process from one state of equilibrium to another state of equilibrium to be an adiabatic process. So what is an adiabatic process? If a material or a system undergoes a change in its physical state in terms of change in the pressure, volume or temperature without any heat being added to it or withdrawn from it, then that particular change is called as adiabatic process. That particular process by which a system undergoes a transition from one state of equilibrium to another state of equilibrium without accepting any heat from the surroundings or without giving away any heat to the surroundings. This process is called as adiabatic process. Now, most importantly, in many of our atmospheric physics discussions, we will take the process to be adiabatic in nature. Right. So, what is an air parcel? Why do we need to consider the control volume to be an air parcel? Air parcel is a small control volume. It is like in fluid mechanics. We take the concept of control volume to describe the motion of fluid from one point to another point, or to describe physical processes that happen within the fluid. We take the idea of air parcels. So rather than considering the entire volume of the fluid, and to be able to write an equation of motion for the fluid is tedious, because fluid system is completely different in comparison to a rigid body or in comparison to a mass of a point mass. Right. So in fluid mechanics, what we do is we consider an infinitesimally small volume of the fluid, and we apply the laws of physics or the laws of conservation of mass, momentum or energy onto this small volume of fluid, and we extrapolate the equations of motion that we get out of this small control volume to the entire fluid. So the idea is, let us say we want to apply the conservation of mass for the fluid. Then what do? Is we take a small control volume, then we equate the amount of fluid that is going into this control volume and the amount of fluid that is going out of the control volume. Then if both are equal, then there is no accumulation of fluid inside the control volume naturally, right? So like that, we always conserve energy, momentum and mass on this small control volumes. And these control volumes can be of two types, a Lagrangian control volume and a Eulerian control volume. So without going into much details, I can simply say that an Eulerian control volume is the one which is fixed with respect to the movement of the fluid. That means the volume will stay in the fluid as it is at the same point, but the fluid will flow or will transfer from one point in the control volume to another point. So the control volume is fixed in space, but in a Lagrangian control volume type, you have the control volume which is kind of moving with the fluid. Right. So this is the basic difference. So why are we talking about control volumes here? Air parcel is also a control volume under certain conditions. We take certain conditions over which the air parcel approximation or the theory is valid. Let us see what are those conditions. Okay. So the environment, we take a smallest possible volume of air in the atmosphere, we call it as air parcel. Now if this is a volume of air, is the volume of air allowing mass transfer? Is the volume of air allowing energy to be transferred inside and to the outside? Is the volume moving with respect to the height? Is the volume having different pressures at different heights? Or is the volume having the same pressure at any different height? These are the questions that we should answer before we take up the approximation of air parcel, right. So air parcel is a small control volume such that the environment where the air parcel is situated is in hydrostatic equilibrium. So what is hydrostatic equilibrium? Hydrostatic equilibrium is the condition where a force balance occurs between the vertical pressure gradient force and the gravitational pull due to the earth, right. So you take control volume in a case where hydrostatic equilibrium is valid, right. So air parcel is not allowed to randomly escape, right. So that is the basic idea, right. Then what else? The parcel does not mix with its surroundings. So it means that the constituents or the contents of the air parcel are not going away, or the constituents of the environment are not mixing well with the air parcel. The basic idea, right. The parcel's movement does not disturb the environment. This is the most, see if this is an assumption, it has to be like this. The parcel's movement does not disturb the environment. So environment stays as it is. The thermodynamical variables describing the nature or the state of environment are not going to be influenced by the movement of the parcel. And the parcel's rise and sink are adiabatic in nature. So parcel is of course in the atmosphere, in the environment. Now this environment is in hydrostatic equilibrium, and the parcel is not rising or sinking at the expense of energy. Rather, it is rising and sinking in an adiabatic nature. So its rise is not due to the heat that is taken up from the system, from the environment. Its sink does not give away energy into the system, right. So the parcel is completely adiabatic in nature. So it is a closed parcel which is not allowing energy transfer by the walls of the volume, right. Most importantly, this is the most important assumption that is very important for us to understand the stability of atmosphere. So we will use this assumption, or we will talk about this assumption in many different ways while we discuss the stability, the cloud formation, and these things, right. So at any given level, at any given height in the atmosphere, the parcel and the environment are at the same pressure. So the point is, if the parcel is at a particular pressure of, let's say, 100 HPA, okay. Now this atmosphere is in hydrostatic equilibrium, right. This atmosphere is in hydrostatic equilibrium, and this parcel that you take at this particular height is also having the same pressure of 100 HPA. Now if it rises, it is not taking energy, inside, or if it sinks, it is not giving away energy as it sinks. So it is perfectly adiabatic, right. But as it rises, it is still at the same pressure as the surroundings. So the natural question that should come into your thought is that what will happen to the volume of the air parcel? Because the pressure, if the pressure decreases, the volume cannot be the same, right. So to compensate the decrease in the volume, the pressure has to increase, right. So, these two things always work together. Right. So, based on our understanding of air parcel, we will and the dry static energy, we will try to see what is the dry adiabatic lapse rate. What is lapse rate? So, dry adiabatic lapse rate is generally given as gamma d with a suffix d, indicating the dry adiabatic lapse rate. So, what is dry adiabatic lapse rate? The rate of change of temperature with respect to the height of a parcel of dry air is called as the lapse rate, right. So, now why do we call it as adiabatic? Because we have assumed that the air parcel rise or sink is perfectly going to be adiabatic in nature, right. And why should the temperature decrease? The temperature inside the air parcel, if at all, if it is not accepting any energy from the outside, the rise should be fueled by the decrease in the internal energy of the air parcel. If the internal energy decreases, the temperature of the air parcel will also decrease. So, as a natural consequence, as the air parcel rises, its temperature will decrease inside. So, but that is why we call it as a lapse rate, because it signifies the decrease in the temperature, and we also call it as the adiabatic because it is not accepting any heat from the system, from the surroundings, right. So, let us say, so to be able to force adiabatic nature, the air parcel undergoes a change such that dq is equal to 0. So, dq is what is dq? dq is the heat that is taken or given out, right. So, the atmosphere is in hydrostatic equilibrium. So, now we just have to combine dq is equals to du plus dw, where dq is already taken to be 0, and it is under hydrostatic equilibrium. So, dp by dz is equals to minus rho g. So, these two equations are the ones. So, by combining these two equations, we can probably get the rate of change of temperature with respect to height. That is it. So, this is the basic idea. So, this rate of change of temperature with respect to height is called as the dry adiabatic lapse rate. Okay. So, under these conditions, so we already seen that under these conditions, the dry static energy, which is what is dry static energy? Dry static energy is H plus what phi. The dry static energy is the sum of enthalpy and the geopotential. What is geopotential? H is enthalpy is the total heat content of the system, and the geopotential at any given height is defined as the amount of work that should be done to rise the air parcel to that particular height from the surface, right. So, under these conditions, what are the conditions? If it is hydrostatic, if the atmosphere is hydrostatic in nature, and if the air parcel is adiabatic in nature, then under these conditions, we have already seen that the dry static energy will remain conserved. So, the rate of change of this dry static energy will be 0, right. So, this will come handy when we deriving a relation for the adiabatic lapse rate. So, the dry static energy is H plus phi, dq is equals to d of H plus phi, because dq is 0, change in the dry static energy H plus phi is equals to 0. So, Cpt plus phi is equals to 0. So, we also know from the geopotential that d phi is equals to minus dz, right. So, we substitute this into this. So, basically Cp dt minus g dz is equals to 0. This is the basic idea, right. So, Cp dt is equals to g dz. So, dt over dz is, this is the minus g by Cp, or dt by dz, we put a minus to signify the decrease in the temperature. So, the rate of change of temperature with respect to z is the altitude here, right. So, dt, the rate of change of temperature with respect to the altitude is equal to g over Cp. So, g is known to be G is known to be 9.81 meters per second square, and Cp is the specific heat at constant pressure. Specific heat at constant. So, we already discussed what are specific heats at constant pressures and at constant volumes, right. So, the rate of change of temperature as it rises, as the air parcel rises, maintaining a constant value of dry static energy will be equal to G over Cp, which is also called as the gamma D. Gamma D is the dry adiabatic lapse rate. So, as the air parcel rises, its temperature decreases with height. So, gamma d, the gamma d is defined to be a positive quantity. Understand? I mean, we keep a minus to signify the decrease in the temperature, right? So, substituting the values of G is equals to 9.81 meters per second square and Cp is equals to 1004 joule per Kelvin per kg. If we substitute this, we will get gamma d as the dry adiabatic lapse rate as 0.0098 Kelvin per meter. I mean, for every meter that you travel up, the temperature will decrease by 0.0098 Kelvin, right, or 9.8 Kelvin per kilometer. So, this is the basic lapse rate that we have discussed in the very beginning while we were discussing the layers of atmosphere, where I said the atmospheric, the troposphere, the bottommost layer of the atmosphere exhibits the negative slope between temperature and the height. That means temperature decreases as you go up. So, and the rate at which this temperature decreases is mentioned to be called as the adiabatic lapse rate. So, here, so if the atmosphere is dry, completely dry, that means there is no moisture in it, then this value of Cp that you have taken makes sense. So, in that case, it will be nearly 10 degrees Celsius or Kelvin per every kilometer. So, as you travel up, for every kilometer that you travel, the temperature in the atmosphere will decrease by 10 degree centigrade, right. So, what is more specific is, I mean, how is this value specific to Earth's atmosphere, let us say. If you, because the dry air, dry air could be taken on any other planet, but how is this 10 Kelvin per kilometer specific to the planet Earth is in terms of its, let us say, gravity and the value, and this Cp evaluated at a constant pressure. What is the pressure and what are the number of atoms or molecules in the dry air that you're talking about, right. So, this is something about the dry adiabatic lapse rate. So, always remember gamma d is equals to minus G over Cp, not Cv, Cp, the dry adiabatic lapse rate. So, this lapse rate is valid for completely dry atmosphere, which never exists, right. There is always an amount of moisture, right. So, most important is that gamma d is the rate of change of temperature following an air parcel of dry air that is being raised or lowered adiabatically in the atmosphere. That means, if you take an air parcel at, let us say, 10 kilometers, if you bring it down, its temperature should increase, right, if its temperature should increase. So, that means that if you take an air parcel from the ground to a level, or the other way, the temperature should compensate in the same way, right. So, the actual lapse rate as measured by different instruments such as radio sonde, they do not converge at, let us say, 10 degrees Celsius per kilometer, rather it is 6 to 7 degrees Celsius per kilometer. And this dry adiabatic lapse rate varies from different from a location to another location. So, there are several processes which will contribute in deciding the average adiabatic lapse rate at a given location, because let us say, for example, if this location is over a hilltop, then you measure the dry adiabatic lapse rate, it will be different. If you measure this dry adiabatic lapse rate on a location near the sea surface, it will be different. So, like that, if you measure it in the tropics, it will be different. If you measure in the poles, it will be different. So, like that, so there are many factors which will decide the rate at which the temperature should decrease with respect to height in the atmosphere, right. So, let us say, so now we talk about a very important physical quantity which is called as the potential temperature, right. There are a few more temperatures that we are going to talk. So, first we have the temperature T, which gives the measure of the energy that the system has, or the gas has in terms of kBT, right. Then we have seen what is called as the virtual temperature. So, virtual temperature was defined as the temperature to which you heat dry air so that it has a density of moist air. So, virtual temperature is always greater than the original temperature because we have a denominator which is less than 1, right. So, here so Tv is the virtual temperature, T is the temperature, E is the vapor pressure, that is because of the moisture, P is the total pressure, epsilon is the ratio of the mean molecular weights or ratio of the gas constants, right. So, here we are going to define another temperature which is called as the potential temperature. So, the potential temperature is denoted by theta, is denoted with theta. Potential temperature of an air parcel is defined as the temperature that the air parcel would have if it were expanded or compressed adiabatically from its existing pressure and temperature to a standard pressure 1000 HPa, the surface pressure, right. So, what it means? I mean, let us say if you take an air parcel, okay. Now, this is the surface where the pressure is standard pressure P naught, the surface pressure, the mean sea level, let us say. If you take an air parcel, now if you want this air parcel to have this pressure, what should you do? You should do, I mean, this is at a height, already at a particular height h, okay. Now, if you want this, so obviously this the pressure P here is less than P naught. Now, if you want this air parcel to have this pressure, what should you do? You should compress it. So, the pressure increases. When you compress it, of course, you are bringing this pressure to this value P naught, but at the same time, due to the compression, the temperature will be increased, right. So, the new temperature that has been increased, I mean, the new temperature that has been achieved just in an effort to reach the standard atmospheric pressure is called as the potential temperature. Now, look at it the other way. If this air parcel is already at a higher pressure, then if you want to reach this pressure, I mean a lower pressure, you have to expand the air parcel. Now, when you expand the air parcel, you are in an adiabatic process. What happens? When you expand it, automatically the pressure will decrease, the volume has increased. On pressure, due to the pressure decrease, the temperature will decrease, right. The new temperature that you are going to achieve at the end of a process in which you are just trying to attain mean sea level pressure is called as the potential temperature. Okay, so we can derive a simple expression for the potential temperature of an air parcel in terms of its pressure P. What is this pressure? Pressure is P is the initial pressure, and P naught, the mean sea level pressure, is referred to as P naught. The initial temperature is T, and the final temperature when you achieve P naught is theta, which is the potential temperature, right. So, from the first law of thermodynamics, we can say Cp dt, which is du, and this is dw, dq is equals to du plus dw, right. So, the heat that is given will increase the internal energy and also do some work, right. So, if you take the picture to be adiabatic in nature, you will simply write dq is equals to 0, right. So, from the ideal gas law, which is P alpha is equals to RT, which is written here, we take d of P alpha. So, we can write alpha is equals to RT by P. So, alpha is RT over P. So, in this expression in terms of alpha, we substitute this RT by P. So, Cp dt minus RT by P, dP is equals to 0, or Cp by R dt over T. So, multiplying this expression with P by RT, we will get Cp by R into dt by T minus dP by P is equals to 0, right. Now, this expression looks like you want to address change in the pressure with respect to pressure and change in the temperature with respect to temperature. You want to address that. This expression, we have got it into a convenient form, right. So, now integrating this expression, so the same thing, we had this expression Cp by R into dt over T is equals to dP over P. So, this expression we integrate from let us say from upward from the pressure surface. So, P naught to P. So, if you get P naught starting from a pressure P, your initial temperature must have been T, but when you reach P naught, the temperature will become theta, right. So, if you integrate this, Cp by R into integral of theta to T dt over T. So, simple integral. So, Cp by R ln of T by theta is equals to ln of P by P naught. So, if you get rid of the ln terms on either sides, so T by theta into Cp T by theta rise to the power of Cp by R is equals to P by P naught. Then it means theta is given as temperature times P naught by P into R by Cp, where what is R? R is the universal gas constant, Cp is the specific heat at constant pressure, P naught is the surface pressure or the standard pressure, P is the pressure at a temperature T, and theta is the final temperature. So, potential temperature is defined as that value of temperature that you will get if you rise or sink an air parcel so that it reaches the standard pressure. So, this equation is called as the Poisson's equation. So, this it is very important that we keep this equation handy if you want to analyze any weather maps or things like that. So, it is called as Poisson's equation. In this equation, we can generally take R is equals to RD is equals to 287 joule per Kelvin per kg. The specific heat at constant pressure, the dry specific heat is 1004 joule per Kelvin per kg. So, this ratio becomes 0.286, right. So, the parameters that remain conserved during a physical, during a physical process are known to be conserved. I mean, parameters that remain constant during a physical process are known to be conserved. So, potential temperature theta remains conserved for an air parcel that moves around in the atmosphere under adiabatic condition, right. So, what else is conserved? So, if the air parcel is moving adiabatically any height to any height, so according to the assumptions itself, we took that pressure will be a constant, right. Now, the pressure, if it is not constant, I mean, we have also seen that H plus phi is also a constant. Now, we are taking one more physical parameter which also remains conserved. This parameter is called as the potential temperature. Potential temperature theta is conserved, right. So, I take change in these quantities, it will be 0, right. So, this was something about the basic thermodynamics, extension of the things that we have been discussing, right. So, I will stop here. So, we will try to see how these parameters will change when we add some amount of moisture.